Hello, in this lecture we will find out the radius of the small circle. In the drawing we have a big semicircle. Inside this big semicircle we have two smaller semicircles and one small circle. We know that this line segment is equals to 140 units in its length, and this line segment equals to 70 units in its length, and our mission is to find out the radius of this small circle. Okay, so first of all we will define the relevant points with names, with letters. So we will define this point as point A. We will define the center of this semicircle as point B. We will define the touching point of the two semicircles with each other as point C. We will define the center of the biggest semicircle, this point as point O. We will define the center of the smallest semicircle as point T. And we define the touching point of the smallest semicircle with the biggest semicircle as E. And we define the touching point of the small circle with the smallest semicircle as G. We define the center of this small circle as F. We will define the touching point of this semicircle and this circle as H. And finally we will define the touching point of the small semicircle with the biggest semicircle here, this point, as I. We also define the center of the we define the radius of the biggest semicircle as capital R and the radius of this small circle as small r. So write it down. According to our definition, capital R is the radius of the biggest semicircle and small r is the radius that we are looking for, is the radius of the small circle. Okay. It has given us the question that this line segment AE equals to 140 plus 70 units. So I write it down. Line segment AE equals to 140 plus 70 units. 140 plus 70 is 210 units, so line segment AE equals to 210 units in its length, But what is line segment AE? From the drawing, it is very easy to see that line segment AE is the diameter of the biggest semicircle. Okay? And the diameter of any circle or semicircle is twice as long as the radius. And because of the fact that the radius of the biggest semicircle equals to capital R, it means that the diameter must be equal to 2 times capital R. So I write it down. AE is the diameter of the biggest semicircle, and it is equal 2 times capital R. 2 times the radius of the biggest semicircle. So from this equation, 2R equals to the diameter of the biggest semicircle equals to AE equals to 210, we will derive that 2 times capital R equals to 210 units. Here we will divide this equation by 2, and we get that capital R equals to 210 over 2, it is 105 units. So we found out that the radius of the biggest semicircle, capital R, equals to 105 units. Okay. Point O is the center of the biggest semicircle. Point A is a point on the semicircle and the biggest semicircle itself. This is exactly the definition of a radius. So OA is the radius of the biggest semicircle that is actually equals to 105 units in its length. Likewise, point O is the center of the biggest semicircle, point E is a point on the biggest semicircle itself. Therefore, OE is the radius of the biggest semicircle that is equal to 105 units in its length. Okay. It is given us the question that line segment AC equals to 140 units in its length. But what is line segment AC? Line segment AC is the diameter of this semicircle. And because of the fact that the diameter of this semicircle equals to 140 units, it means that the radius must be equal to half of it. That is to say, the radius AB of this semicircle must be equal to 140 over 2, that is to say, it is 70 units. And the radius BC also must be equal to 70 units in its length. Likewise, it is given us the question that line segment CE equals to 70 units in its length. But what is line segment CE? Line segment CE is the diameter of the smallest semicircle. This smallest semicircle. And because of the fact that the diameter of the smallest semicircle equals to 70 units, it means that the radius must be equal to half of it. That is to say, 70 over 2 is 35. So CD, the radius of the smallest semicircle, equals to 35 units in its length. And DE is also the radius of this semicircle that must be equal to 35 units in its length. Okay. And what is the length of line segment BO? From the drawing, it is very easy to see that OB, BO, OB, doesn't matter, OB, line segment OB equals to OA minus BA. Again, OB equals to OA minus BA. Repeat again. Line segment OB or BO equals to OA minus BA. So BO equals to OA. OA is the radius of the biggest semicircle, that's equal to 105 units. So we substitute OA by 105 units minus BA. BA is the radius of this semicircle, that is equal to 70 units in its length. So we substitute BA by 70. In conclusion, we found out that BO or OB, does it matter, equals to 105 minus 70, that is 35 units. Line segment BO equals to 35 units in its length. So we can write down in the drawing that line segment BO equals to 35 units in its length. Okay. Likewise, we'll find out the length of line segment OC. From the drawing, it is very easy to see that OC equals to OE minus CE. Again, OC equals to OE minus CE. OC equals to OE minus CE. So OC equals to OE is the radius of the biggest semicircle, that is equal to 105 units. So we substitute OE by 105 minus CE. CE equals to 35 plus 35 units, that is 70 units. So we will substitute CE by 70. In conclusion, we found out that the length of line segment OC or CO, it is 105 minus 70, that is also 35 units. So we can write down that CO equals to 35 units in its length. This line segment OC or CO equals to 35 units in its length. Okay. In the next step, I will present to you two new rules. And we will implement the two new rules in our drawing. We have rule number 10. According to rule number 10, if two circles are touching each other internally, so in this drawing, the small circle is located inside the big circle. And therefore, it is defined here that the two circles are touching each other internally at point N. Okay? So if two circles are touching each other internally, like in this drawing, then the straight line that connects their centers together, the center of the big circle is at point O, the center of the small circle is at point M, and the straight line that connects their centers together is OM. This straight line OM, according to rule number 10, must pass through their touching point. Their touching point is here at point N. So the straight line OM must pass through point N. That is to say, OMN is one straight line. Again, OMN is one straight line. Okay? And what is the distance between their centers? The distance between the centers of the two circles is OM. And what is the value of OM? What is the length of OM? From the drawing, it is very easy to see that the length of line segment OM equals to NO minus NM. Again, NO minus NM equals to MO. So NO equals to capital R, that is the radius of the big circle, and m equals to small r, that is the radius of the small circle. In conclusion, we found out that mo equals to capital R minus small r. Okay, the distance between their centers, it is equal to capital R minus small r, or mo equals to capital R minus small r. So we can summarize and say that whenever we have an internal notch between two circles, that is to say the two circles are touching each other internally, in this case it is at point N, then the straight line that connects their centers together must pass through their touching point. That is to say, the straight line OM must pass through point M for point N, therefore OMN is one straight line, and in addition, you know that the distance OM between their centers equals to the difference between their radii. The radius of the big circle is capital R, the radius of the small circle is small r, and the difference between the radii is capital R and small r. Okay, and we also have rule number 11. According to rule number 11, if two circles are touching each other externally, in this drawing, none of those two circles are inside the other one, therefore it is defined that the two circles are touching each other externally at point N. Point N is their touching point or point of tendency. Then the straight line that connects their centers together, the center of the big circle is here at point O, the center of the small circle is here at point M, and the straight line that connects their centers together is OM, of course. This straight line OM, according to rule number 11, must pass through their touching point. Their touching point here is here at point N, so OM must pass through point N, or O and M is one straight line. Again, O and M is one straight line. Okay? And what is the distance between their centers? The distance between their centers is OM. And this distance OM, from the drawing, it is very easy to see that because of the fact that O and M is one straight line, it means that OM equals to ON plus NM. Again, OM equals to ON plus NM. ON is capital R, NM is small r. Therefore, OM equals to capital R plus small r. So we can summarize and say that whenever we have an external notch between two circles, that is to say the two circles are touching each other externally, in this case it is point N, then the straight line that connects their centers together must pass through their touching point. In this case, the straight line OM must pass through point N, that is to say O and M is one straight line, and the distance between their centers OM equals to the addition of the two radii with each other. That is to say it is capital R plus small r. Okay, so we can actually implement the two new rules in our drawing. This circle have an external notch with this semicircle at point edge. That is to say, the circle and the semicircle are touching each other externally at point edge. And therefore, according to rule number 11, and the center of this semicircle is point B, and the center of this circle is here at point F. Therefore, according to rule number 11, the straight line that connects the centers together, that is to say FB, must pass through their touching point, or BHF is one straight line. Again, BHF is one straight line. because of the fact that BHF is one straight line, the distance BF between their centers will be equal to edge F. Edge F is the center of this small circle, edge is a point on this small circle itself. Therefore, F edge is the radius of this circle that is defined as small r. Likewise, point B is the center of this semicircle. Point H is a point on this semicircle itself. Therefore, this is exactly the definition of a radius. So BH is the radius of this semicircle, and the radius of this semicircle equals to 70 units. In conclusion, we found out that the length of line segment FB is R plus 70 or 70 plus R units. So I write it down. FB equals to R plus 70 units. $70 plus R units. And 70 plus R units, it is the addition of the two radii with each other. The radius of this circle is 70, the radius of this circle is R, and 70 plus R is the addition of the two radii with each other, exactly according to rule number 11. Likewise, we have this circle have an external notch with this small semicircle at point G. That is to say, they are touching each other externally at point G. Therefore, according to rule number 11, the straight line that connects their centers together is FD. Why? Because F is the center of this small circle, and D is the center of the smallest semicircle. Therefore, FD is the distance between their centers, and FD is the straight line that connects their centers together. And according to rule number 11, the straight line that connects their centers together, FD, must pass through their touching point. Their touching point is here at point G. Or FGD is one straight line. FGD is one straight line. And because of the fact that FGD is one straight line, it means that the length of FD, or the distance between their centers FD, equals to FG, here point F, FG plus GD. So what is FG? Point F is the center of this small circle. Point G is a point on the small circle itself. Therefore, FG is the radius of this small circle, that is equal to small r, plus GD. Point D is the center of the smallest semicircle, this smallest semicircle. Point G is a point on this small semicircle itself. Therefore, GD is the radius of this smallest semicircle, that is equal to 35 units. So we found out that FD, that is the distance between the centers of this small circle and the smallest semicircle, equals to 35 plus R units. I write it down. FD equals to 35 plus R units. FD equals to 35 plus R units, and 35 plus R units, it's actually the addition of the two radii with each other. The radius of the smallest semicircle is 35 units, the radius of the small circle is R, and the addition of the two radii with each other is 35 plus R, exactly like rule 11, that whenever it says that whenever you have an external notch between two circles or semicircles, the straight line that connects their centers together, that is to say FD, must pass through their touching point, that is to say for point G, or FGD is one straight line, and the distance between their centers FD equals to the addition of the two radii with each other, that is to say R plus 35 is equal to FD. Okay. What is the length of line segment BD? B is the center of this semicircle, D is the center of the smallest semicircle, so BD is the distance between the centers of the two semicircles, and those two semicircles have an external arc between them at point C. Therefore, according to rule number 11, the straight line that connects their centers together is BD. And BD must pass through their touching point, that is actually point C, or BCD is one straight line. BCD is one straight line, and the distance between their centers must be equal to the addition of the two radii with each other. Or, from the drawing, it is very easy to see also that BCD equals to BC plus CD. BC is 35 plus 35 is 70, CD is 35 units, therefore in total BD equals to 70 plus 35 units. 70 plus 35 units, that is actually 105 units. And 105 units is the distance between their centers. That is also equals to the addition of the two radii with each other. The radius of this semicircle is 70, the radius of this smaller semicircle is 35, and the addition of the two radii with each other is 70 plus 35, that is 105 units. So in conclusion, we found out that line segment BD equals to 105 units in its length. Likewise, we have an internal notch. First of all, this small circle is located inside the biggest semicircle, and therefore they have an internal notch between them at point I. That is to say, they are touching each other internally at point I. And therefore, according to rule number 10, whenever we have an internal notch between two circles or semicircles, the straight line that connects their centers together must pass through their touching point. The center of the biggest semicircle is here at point O. The center of this small circle is here at point F. So the straight line that connects their centers together is OF. And according to rule number 10, the straight line OF must pass through their touching point. That is to say, through point I. Or OFI is one straight line. Again, OFI is one straight line. And the distance between their centers is FO. FO. And according to rule number 10, the distance between their centers, in this case FO, must be equal to the difference between their radii. The radius of the biggest semicircle equals to capital R. The radius of this small circle is small r. And the difference between the radii is capital R minus small r. In conclusion, we found out that FO equals to capital R minus small r. Again, FO equals to capital R minus small r. But we have already found out that capital R equals to 105, so we substitute capital R by 105 units. Minus r, minus small r is the radius that we are looking for. In conclusion, FO equals to 105 minus r units. You can see it on, so here, point F is the center of this circle, point I is the point on this circle itself, therefore Fi equals to small r. This is the radius of this small circle. You can see it also from the drawing itself that FO equals to OI minus IF. OI is the radius of the biggest semicircle, that is capital R, and IF is small r. That is to say, FO equals to capital R minus small r, that is 105 minus small r units. Okay, so in the next step, I will present to you a new rule, and we will implement the new rule in triangle FBD. And repeat again. we'll implement the new rule in this ring triangle, triangle FVD. We have already found out the sides of this triangle, and also we found out that FO, this line segment FO, equals to 105 minus R units. Okay. The new rule is called Stewart's Theorem. Stewart's Theorem. And it is true in any triangle. So the triangle that I will draw could be any triangle. This triangle, triangle ABC, could be any triangle. This is triangle ABC. We know that the length of line segment AB is A units. Line segment, the length of side AB is A units. Side AC of triangle ABC equals to B units in its length. And side BC equals to C units in its length. In addition, we have also line segment AO. This line segment AO equals to D units in its length. We also know that line segment BO equals to M units, and finally line segment OC equals to N units in its length. Okay. Then, according to Stewart's theorem, in this triangle ABC, that could be any triangle, the following equation is true. A squared times n plus b squared times m equals to C. C is the length of side BC. We will open the brackets here, and inside the brackets we have d squared plus m times n. Here we close brackets. I repeat again, according to Stewart's theorem, this triangle ABC, that could be any triangle. A squared times n plus b squared times m equals to C. We will open brackets here. Inside the brackets we have d squared plus m times n. Okay. So we can actually implement Stewart's theorem, the new rule, in our ring triangle, triangle BFD or FBD. So I copy triangle FBD in a new page, and we will implement on it Stewart's theorem. This is triangle FBD that occurs from the original drawing. We have already found out that side FB equals to 70 units plus R, 70 plus R units in its length. Side FD equals to 35 plus R units in its length. And finally, side BC, this side BC, side BD, it is side BD actually, equals to 105 units in its length. In addition, we have also line segment FO, line segment FO, this is line segment FO, that is equal to 105 minus R units in its length. FO equals to 105 minus R units. And what is the length of line segment BO? From the drawing it is very easy to see that BO equals to 35 units in its length. So here BO equals to 35 units in its length. And finally, what is the length of line segment OD? From the drawing it is very easy to see that OD equals to OC plus CD. OC is 35, CD is 35. Therefore, OD in total equals to 35 plus 35, that is 70 units. Here, OD equals to 70 units in its length. So, we will implement in this triangle FBD, Stewart's theorem. According to Stewart's theorem, in this triangle FBD, we will get that FB square times OD, FB square times OD plus FD square times BO equals to BD. Here we'll open brackets. Inside the brackets we have FO square plus BO times OD. BO times OD. Here we'll close the brackets. So this equation is the implementation of Stewart's theorem in our triangle FBD. Repeat again, according to Stewart's theorem in our triangle FBD, FB squared times OD plus FD squared times BO equals to BD. We open the bracket, inside the brackets we have FO squared plus BO times OD. Okay, so here FB equals to 70 plus R, therefore FB squared is 70 plus R squared times OD. OD is 70 units, so we substitute OD by 70 plus FD squared. FD squared is 30, FD is 35 plus R, therefore FD squared is 35 plus R squared times BO. BO is 35, so we substitute BO by 35. Okay, so in this other equation we have 70 plus R squared times 70 plus 35 plus R squared times 35. and it is equal. In the other side of the equation we have BD. BD is 105, so we substitute BD by 105. And here we open brackets. Inside the brackets we have FO squared. FO is 105 minus R, therefore FO squared is 105 minus R squared. 105 minus R squared plus BO is 35 times OD is 70. Okay. In conclusion, we found out that according to Stewart's theorem, in triangle FBD, 70 plus R squared times 70 plus 35 R squared times 35 equals to 105. We open brackets here. Inside the brackets we have 105 minus R squared plus 35 times 70. In the next step, we'll define the number 35 as x. 35 equals to x according to our definition, and we'll substitute in this equation any number that is equal to 35, or any multiplication of 35 by a natural number. We'll substitute it by x, and we'll get that here we have 70 plus R squared times 70. 70 is 2 times 35. 2 times 35 is 2x according to our definition, because x equals to 35. So 70 is 2x plus R squared times 70 is 2x plus 35 plus R squared is x plus R squared times 35 is x. So we substitute 35 by x is equal to 105. 105 is 3 times 35, that is to say it is 3x. Here we open bracket. Inside the brackets we have 105, that is 3x, minus R squared plus 35 is x, and 70 is 2x. Here we'll close brackets. Okay. So this is the equation that we got after we substituted x by x or any multiplication of, after we substitute 35 or any multiplication of 35 by natural number by x. 2x plus R squared times 2x plus x plus R squared times x equals to 3x. We open brackets. Inside the brackets we have 3x minus R squared plus x times 2x. Here we close the brackets. Here we'll divide this equation by x. So here x will get cancelled. Here also x will get cancelled, and here also x will get cancelled. So what is left from this equation after we cancel x? We have here 2 times 2x plus R squared plus x plus R squared equals to 3. We open brackets here. Inside the brackets we have 3x minus R squared plus x times 2x is 2x squared. Here we close the brackets. So this is the equation after we divided the original equation by x. Here we will open the brackets on this side of the equation. We have here 2, and we have 2 times 2x plus R squared. 2x plus R squared equals to 2x squared, that is 4x squared, plus r squared, plus 2 times 2xr is 4xr. Okay. And we also have here plus x plus r squared. X plus r squared is x squared plus r squared plus 2xr equals to, in the other side of the equation we have 3 and we open brackets here. Inside the brackets we have 3x minus r squared according to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. We get that 3x minus r squared equals to 3x squared, that is 9x squared, plus r squared minus 2 times 3xr is minus 6xr, plus 2x squared. Here we close the brackets. Here we'll open the brackets on this side of the equation. We have 2 times 4x squared is 8x squared, plus 2 times r squared is 2r squared, plus 2 times 4xr is 8xr, plus x squared plus r squared plus 2xr equals to 3 times, we open brackets here, inside the brackets we have 9x squared plus 2x squared is 11x squared, plus r squared minus 6xr. Here we close the brackets. On this side of the equation we have 9x squared plus x squared, 8x squared. This is 8x squared plus x squared is 9x squared. 2r squared plus r squared is 3r squared. (10xr plus 2xr and 8xr). This is 8xr plus 2xr is 10xr. So, in conclusion, in this side of the equation we have 9x squared plus 3r squared plus 10xr, and it is equal to, here we'll open the brackets and we'll get that 3 times r squared is 33x squared plus 3r squared (3 times minus 6xr is minus 18xr). So in total, in conclusion, this side of the equation we have 33x squared plus 3r squared minus 18xr. So we have 3r squared on both sides of the equation. So 3r squared will get cancelled. What is left from this equation after we cancel 3r squared? In this side of the equation we left only with 9x squared plus 10xr. That is equal. On the other side of the equation we left only with 33x squared plus, minus 18xr. Here we'll subtract 9x squared from this equation and we'll get that 9x squared minus 9x squared is 0. So in this side of the equation we left only with 10xr. In the other side of the equation we have 33x squared minus 9x squared is 24x squared minus 18xr. In conclusion, we found out that 10xr equals to 24x squared minus 19xr. Here we will add 18xr to this equation and we'll get that 10xr plus 18xr is 28xr. That is equal to 24x squared, and 18x squared minus 18x squared is 0. So in this side of the equation, we have to live with 24x squared, or in conclusion, found out that 28xr equals to 24x squared. Here we will divide this equation by x, and we will get that 28xr over x is 28r. That is equal to 24x squared over x is 24x. So here we will substitute x by 35. According to our definition, 35 equals to x, therefore we substitute x by 35, and we will get that 28xr equals to 24 times x, and x is 35. So we substitute x by 35. So in conclusion, we found out that the 28xr equals to 24 times 35. Here we will divide this equation by 7, and we will get that 28 over 28. It is actually, we have here 28r equals to 24 times 35. We'll copy it again. 28r equals to 24 times 35. Here we will divide this equation by 7, and we get that 28 over 7 is 4. So in total, in this side of the equation, we have 4r, and it is equal to 24 times 35 over 7 is 5. So in total, in this side of the equation, we have 24 times 5. So 4r equals to 24 times 5. Here we will divide this equation by 4, and we get that 4r over 4 is r. So in this side of the equation we have r, and 24 over 4 is 6. In total, in this side of the equation we left with 6 times 5. In conclusion, we found out that r equals to 6 times 5, that is 30. So in conclusion, we found out that the radius of the small circle, the radius that we are looking for, the radius of this small circle r equals to 30 units in its length. R equals to 30 units. In the next step, I will summarize the lecture. In the drawing, we have a big semicircle. Inside this big semicircle, we have two smaller semicircles and one small circle. It is given as the equation that line segment AC equals to 140 units in its length, and line segment CE equals to 70 units in its length. And our mission is to find out the radius of this circle. Okay, first of all, we gave names to the relevant points to this question, and then we defined capital R as the radius of the biggest semicircle, and small r as the radius of this circle. That is the radius that we are looking for. I'll repeat again. Capital R is the radius of the biggest semicircle according to our definition, and small r is the radius of the small circle, that is the radius that we are looking for. It is given us the equation that AE equals to 70 plus 100 units. That is to say, AE equals to 70 plus 140 plus 70 units is 210. So AE equals to 210 units. But what is actually line segment AE? Line segment AE is also the diameter of the biggest semicircle. And because of the fact that the diameter of this biggest semicircle is AE, and the radius, according to our definition, the radius of the biggest semicircle equals to capital R. Therefore, the diameter must be twice as long as the radius. That is to say that the diameter of this biggest semicircle must be equal to 2 times capital R. Okay, so we found out that AE is also the diameter of the biggest semicircle, and because of the fact that the radius of the biggest semicircle equals to capital R according to our definition, therefore the diameter must be equal to twice of the radius. That is to say, the diameter must be equal to 2 times capital R. And from this long equation, 2 times capital R equals to the diameter equals to A equals to 210, we will derive that 2R equals to 210. 2R equals to 210. We divided this equation by 2 and we found out that capital R equals to 105 units. Capital R, that is the radius of the biggest semicircle, equals to 105 units. So AO is the radius of the biggest semicircle and it is equal to 105 units, and OE it is also the radius of this biggest semicircle that is equal to 105 units. Okay? Then it is given as the equation that line segment AC equals to 140 units in its length. But what is AC? AC is the diameter of this semicircle, and if the diameter equals to 140, it means that the radius of this semicircle AB must be equal to 140 over 2, that is 70, and the radius BC must be also equal to 70 units in its length. Likewise, we have line segment CE, it is given us the equation that is equal to 70 units in its length. But what is line segment CE? Line segment CE is the diameter of the smallest semicircle, and if the diameter equals to 70, it means that the radius must be equal to half of it. So the radius CD must be equal to 70 over 2, that is 35 units, and the radius DE of this smallest semicircle must be also equal to 35 units in its length. In the next step, we found out the length of this line segment OB. From the drawing, it is very easy to see that OB, this line segment OB equals to OA minus BA. Again, OA minus BA equals to OB. I'll repeat again. OBO equals to OA minus BA. OA is the radius of the biggest semicircle that is equal to 105 units. BA is the radius of this semicircle that is equal to 70 units. So in conclusion, we found out that BO equals to 105 minus 70, that is 35 units. So here, BO equals to 35 units in its length. Okay, write down here that BO equals to 35 units in its length. This line segment. In the next step, we found out the length of this line segment OC. From the drawing, it is very easy to see that OC equals to OE minus CE. Again, OE minus CE equals to OC. I'll repeat again. OC equals to OE minus CE. OE is the radius of the biggest semicircle that is equal to 105 units. CE equals to 70 units. In conclusion, we found out that OC equals to 105 minus 70, that is 35 units. So CO equals to 35 units in its length. In the next step, I presented to you 2 new rules, and we implemented the 2 new rules in our drawing. We have rule number 10. According to rule number 10, if 2 circles are touching each other internally, because of the fact that the small circle is located inside the big circle, therefore, we can say here that they have an internal knot between them at point N, or they are touching each other internally at point N. Okay? So we have here an internal knot between 2 circles, and according to rule number 10, the straight line that connects their centers together is OM. Why? Because O is the center of the big circle and M is the center of the small circle. Therefore, OM is the straight line that connects their centers together. According to this rule number 10, the straight line OM must pass through their touching point That is to say, for point N, or OMN is one straight line. Again, OMN is one straight line. And what is the length OM? That is the distance between their centers. What is actually the distance between their centers OM? What is the value of OM? From the drawing, it is very easy to see that OM equals to NO minus NM. Again, NO is capital R and NM is small r. So MO equals to capital R minus small r. So whenever you have an internal knot between two circles, then the straight line that connects their centers together must pass through their touching point. That is to say, OM, the straight line the straight line OM must pass through point N. That is to say, OMN is one straight line, and the distance between their centers will be equal to the difference between their radii. In this case, it is capital R minus small r. That is actually rule number 10, and we also have rule number 11. According to rule number 11, if two circles are touching each other externally, in this drawing, none of those two circles are inside the other one. And therefore, it is defined here that the two circles are touching each other externally at point N. So the straight line that connects their centers together is OM. Why? Because O is the center of the big circle, M is the center of the small circle. Therefore, OM is the straight line that connects their centers together. This straight line OM must pass through their touching point. That is to say, to point N. O and M is one straight line. And what is the distance between their centers? The distance between their centers is of course OM. But what is the value of OM? OM equals to the addition of the two radii with each other. The radius of the big circle is capital R, the radius of the small circle is small r, and therefore the addition of the two radii with each other, OM equals to capital R plus small r. I'll repeat again. Whenever you have an external knot between two circles, then the straight line that connects their centers together must pass through their touching points. Here, in this case, OM must pass through point N, or O and M is one straight line, and the distance between their centers, in this case OM, equals to the addition of the two radii with each other. In this case, it is capital R plus small r. We can actually implement the two new rules in our drawing. Why? Because in our drawing, we have this semicircle have an external knot with this semicircle. Those circle and semicircles have an external knot between them at point H. That is to say, they are touching each other externally at point H. And therefore, we can implement here rule number 11. That is to say, the straight line that connects their centers together is FB, because F is the center of this circle, and B is the center of this semicircle. The straight line that connects their centers together is FB. FB must pass through their touching point, that is to say, from point H. That is to say, FHB is one straight line. FHB is one straight line, and what is the distance FB between their centers? It is equal to the addition of the two radii with each other. The radius of this circle is R, the radius of this semicircle is 70, and the addition of the two radii with each other is 70 plus R. In conclusion, we found out that FB equals to 70 plus R units. FB equals to 70 plus R units. Likewise, we have this circle have an external knot with the smallest semicircle at point G. That is to say, the circle and the semicircle are touching each other externally at point G. Therefore, we can implement here rule number 11. According to rule number 11, the straight line that connects their centers together, FD. Why? Because F is the center of this small circle. D is the center of the smallest semicircle. And therefore, FD is the straight line that connects their centers together. According to rule number 11, must pass through point G, or FGD is one straight line. And what is the distance between their centers? The distance between their centers is FD. And according to rule number 11, it is equal to the addition of the two radii with each other. The radius of this small circle is R, the radius of this smallest semicircle is 35, and the addition of the two radii with each other is 35 plus R. In conclusion, we found out that FD equals to 35 plus R units. So repeat again, FD equals to 35 plus R units. And we have also those two semicircles have an external arc between them at point C. That is to say, they are touching each other externally at point C. And therefore, we can implement here again rule number 11. According to rule number 11, the straight line that connects their centers together is BD. Where B is the center of this semicircle, and D is the center of the smallest semicircle, this smallest semicircle. So this straight line BD that connects their centers together must pass through their touching point. That is to say, from point C. Point C is their touching point. Or BCD is one straight line. And what is the distance between their centers? The distance between their centers, it is equal to the addition of the two radii with each other. The radius of this semicircle is 70 units. The radius of this smallest semicircle is 35. And the addition of the two radii with each other will give us 70 plus 35. So, in conclusion, we found out that BD equals to 70 plus 35, that's 105 units. I repeat again, BD equals to 105 units in its length. Then, this small circle is located inside the biggest semicircle, and they have an internal arc between them at point I. That is to say, they are touching each other internally in this point, point I. And therefore, we can implement here rule number 10. According to rule number 10, the straight line that connects their centers together, FO. FO is the straight line that connects their centers together. Why? Because F is the center of this small circle, and O is the center of the biggest semicircle. Therefore, FO is the straight line that connects their centers together. Must pass through their touching point. That is to say, it must pass through point I, that is their touching point. Or OFI is one straight line. Again, OFI is one straight line according to rule number 10. And what is the distance FO between their centers? The distance FO between their centers equals to the difference between their radii. The radius of the biggest semicircle is equal to capital R. The radius of the small circle equals to small r, and the difference between the radii is capital R and small r. I'll repeat again, FO, the distance between their centers, is capital R minus small r. Capital R is 105, so we substituted capital R by 105, and finally found out that the distance between their centers, FO, equals to 105 minus r units. Okay, so in the next step, I presented to you new rule, and implemented the new rule in the great triangle BFD. The new rule is called Stewart's Theorem. According to Stewart's Theorem, Stewart's Theorem is true in any triangle, so this triangle ABC, could be any triangle. We know that the length of side AB is equal to A units, side AC equals to B units in its length, and finally side BC equals to C units in its length. In addition, we know that line segment AO equals to D units in its length, BO equals to M units, and OC equals to N units in its length. Then, according to Stewart's theorem, the following equation is true. A squared times M plus B squared times M equals to C, we open brackets, inside the brackets we have D squared plus M times N. I repeat again, according to Stewart's theorem, A squared times M plus B squared times M equals to C, open brackets, inside the brackets we have D squared plus M times N. We actually can implement the new rule, Stewart's theorem, in our triangle FBD. I copied triangle FBD in this new page. We already found out the size, all the three sides of this triangle. We also found out that FO, line segment FO equals to 105 minus R units. What is the length of line segment BO? BO equals to 35 units, here 35. And OD equals to 35 plus 35, that is 70. So here, OD equals to 70 units and BO equals to 35 units. In the next step, we implemented the Stewart's theorem in this triangle FBD. According to Stewart's theorem, in this triangle FBD, we get that FB squared times OD plus FD squared times BO equals to BD, we open brackets. Inside the brackets we have FO squared plus BO times OD. I repeat again, according to Stewart's theorem, in this triangle FBD, FB squared times OD plus FD squared times BO equals to BD, we open brackets. Inside the brackets we have FO squared plus BO times OD. This equation is the implementation of Stewart's theorem in our triangle FBD. FB is 70 plus R, therefore FB squared is 70 plus R squared times OD. OD is 70, so we substitute OD by 70 plus FD squared. FD is 35 plus R, therefore FD squared is 35 plus R squared times BD. BD is 35, so substitute BD. Actually, it is BO. It is BO. BO is 35, so substitute BO by 35. Okay, and then we have, on the other side of the equation, we have BD. BD is 105, so we substitute BD by 105. Inside the brackets, we have FO squared. FO is 105 minus R, therefore FO squared is 105 minus R squared, plus BO is 35 and OD is 70. Okay. Then we defined 35 as x, and we substituted 35 or any multiplication of 35 by a natural number by x. And we got here that 70 is 2 times 35, that is to say it is 2x. So we substitute 70 by 2x. 70 plus R squared is 2x plus R squared times 70 is 2x. So this expression in total equals to 2x plus R squared times 2x. Plus 35 plus R squared is x plus R squared times 35. 35 is x, so substitute 35 by x. So it is x plus R squared times x, and it is equal to 105. 105 is 3 times 35, and therefore we substitute 105 by 3 times x. Inside the brackets we have again 105, that is 3x, minus R squared, plus 35 is x, and 70 is 2x. So 35 times 70 is x times 2x. Here we divided this equation by x, so x will get cancelled here, x will get cancelled here, and also x will get cancelled here. So what is left from this equation after we cancelled x? We have here 2 times 2x plus R squared plus x plus R squared equals to 3. Inside the brackets we have 3x minus R squared plus 2x squared. Okay. Here we open the brackets and we got that 2 times 2x plus R squared equals to 2x squared, that is 4x squared, plus R squared, plus 2 times 2xr is 4xr. And is equal to 3. Inside the brackets we have 3x minus R squared, according to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. We will get that 3x minus R squared equals to 3x squared, that is 9x squared, plus R squared, minus 2 times 3xr is minus 6xr, plus 2x squared. Here we close the brackets. Here we open the brackets again. 2 times 4x squared is 8x squared, 2 times R squared is 2R squared, and 2 times 4xr is 8xr, plus x squared plus R squared plus 2xr. And it is equal to 3 times, inside the brackets we have 9x squared plus 2x squared is 11x squared, plus R squared minus 6xr. Here we close the brackets. In this side of the equation we have 8x squared plus x squared is 9x squared, 2r squared plus r squared is 2r squared, and 8xr plus 2xr is 10xr. In total, in this side of the equation we have 9x squared plus 3r squared plus 10xr equals to, here we open the brackets, 3 times 11x squared is 33x squared, 3 times r squared is 3r squared, and 3 times minus 6xr is minus 18xr. So in this side of the equation, in total we have 33x squared plus 3r squared minus 18xr. Here we have 3xr on both sides of the equation, so 3r squared. We have 3r squared on both sides of the equation, so 3r squared will get cancelled. What is left from this equation after we cancel 3r squared? In this side of the equation we left only with 9x squared plus 10xr. In the other side of the equation we left only with 33x squared minus 18xr. So in conclusion, we found out that 9x squared plus 10xr equals to 33x squared minus 18xr. Here we subtracted 9x squared from this equation, and we got that 9x squared minus 9x squared is 0. So in total, in this side of the equation, we left only with 10xr. In this side of the equation, we have 33x squared minus 9x squared is 24x squared minus 18xr. Here we added 18xr to this equation. 10xr plus 18xr is 28xr. And here we have 24x squared, and 18xr minus 18xr is 0. So what left in this side of the equation is only 24x squared. In conclusion, we found out that 28xr equals to 24x squared. Here we divided this equation by x. Therefore, 28xr over x is 28r, and 24x squared over x is 24x. In conclusion, we found out that 28r equals to 24x. Here we substituted x by 35. X equals to 35 according to our definition. And found out that 28r equals to 24x, and x is 35. So we substituted x by 35. In conclusion, we found out that 28r equals to 24 times 35. Here we divided this equation by 7, and we got that 28 over, here we have 28r equals to 24 times 35. We divided this equation by 7, and found out that 28 over 7 is 4. So in total, in this side of the equation we have 4r, that is equal to 24 times 35 over 7 is 5. In total, in this side of the equation we have 24 times 5. So in conclusion, we found out that 4r equals to 24 times 5. Here we divided this equation by 4, and we got that 4r over 4 is r. So in this side of the equation we have left only with r, and 24 over 4 is 6. So in this side of the equation we left only with 6 times 5 in total. So in conclusion, we found out that r equals to 6 times 5. 6 times 5 is 30. So in conclusion, we found out that the radius of the small circle, the radius of this circle, that is the radius that we are looking for, r equals to 30 units in its length. Okay, thank you very much.